All right, so previously we got ourselves to a place where we can do partial fraction expansion on this VC of S. So let's go to the next slide here. If you remember correctly, we basically have two different things that we're going to have to do here. We're going to have to solve for A here, and we're going to have to solve for B as well. Let's just make another copy of this. And then we can go ahead and carry out the partial fraction expansion. Probably should plug in values for R and C. Just note that R is equal to 1K from the previous slide. C is equal to 1 microfarad. So therefore, R times C gives us 10 to the minus 3, or 1 over 1,000. So when we plug that in, we can go from there. So first and foremost, in order to solve for A, we need to multiply both sides by S, right? So let's multiply by S on both sides. That causes these to cancel, and then I rewrite this as A plus BS over S plus 1 over RC equals 5 over RC divided by S plus 1 over RC. And then we evaluate both sides at S equals 0, right? If I do that, that causes this term to go to 0. And over here, I evaluate at S equals 0. And this also goes to 0. So what I get is that A is basically going to be equal to 5 over RC divided by 1 over RC, right? In that case, 5 over RC divided by 1 over RC is just 5. So my value for A is just 5. Okay, so that's the first part of my partial fraction expansion. A is done. So now let's solve for B. If we want to solve for B, we know we have to multiply both sides by S plus 1 over RC, right? The denominator of B. That causes these to cancel. S plus 1 over RC here as well. And that's going to cause these to cancel. And so let me rewrite this as B, or sorry, let's just write it out as A times S plus 1 over RC divided by S plus B is equal to 5 over RC divided by S. And now what do? Of course, we evaluate both sides at S equals minus 1 over RC so that we can get the B by itself, right? So let's give me some more room here. I'm going to evaluate this side as S equals negative 1 over RC. That causes this term to go to 0. And I evaluate this side as S equals negative 1 over RC. And so I get B is going to be 5 over RC divided by negative 1 over RC. And that's just going to give me B equals negative 5. All right. And so we've done our partial fraction expansion. So now we can just rewrite our term for VC of S, right? It was originally this function, but now we've done the partial fraction expansion. We can write it as 5 over S minus 5 over S plus 1 over RC. And now we can very easily determine the time domain expression using the Laplace transform. So right off the bat, we probably see that this is going to be, maybe you don't see it, but this is going to be 5 times u of t. And this other one, let's go and look at our Laplace transforms. Something over s plus a. That's this same Laplace transform here. We'll just put this up here. So this is going to be 5 e to the minus a. What is my a? It's 1 over RC, so it's just going to be e to the minus t over RC multiplied by u of t. Wow. Well, does that look familiar or what? So my VC of t is 5 times u of t, basically just saying that it's valid for t greater than 0, remember, multiplied by 1 minus e to the minus t over RC. Does that look familiar or what? That is our charging equation for an RC circuit. So let's see, we can rewrite this as VC of t is equal to 5 times 1 minus e to the minus t over RC volts, and that's valid for t greater than equal to 0 since I have the u of t in there. And this is our standard charging equation for an RC circuit, which is exactly what we should expect from such a circuit. And so we finished this problem. We found VC of t. Much more roundabout sort of way of doing things, but we avoid using differential equations altogether. We use Laplace, and we see how this comes together to give us exactly what we would expect for an RC circuit, right? We've got this step input. We've got our R and our C. We're monitoring this voltage here, and we know that it's going to do this exponential rise with a time constant of R times C, and that pops right out of the math when we do this Laplace transform. I think it's so cool that this works out. Hopefully you also think it's cool that it works out. If you have any questions, obviously, please feel free to let me know. But that pretty much does it for this RC circuit example. And I'll do one more example problem in the next video just to show this process again, but for an RL circuit that time. So we'll see you guys in the next video.